Okay, so in the last lecture we said that if we fix alpha, this is typically the way the test is designed. We fix alpha and then maybe compute beta at a certain value where we want the probability of a type 2 error to be low. We say, okay, if we're this far into the alternative region, I really want to make sure we reject. And if we don't get a satisfactory probability there, the next step is to consider trying to get a bigger sample, because this will reduce it. This will, no matter what it will decrease it. No matter what the parameter is and what it is, it should decrease it. Well, I say that, but in these tests, it should, in these kind of normal large sample tests, this is true. So so let's look at this. So to start, so let's call this picking setting n to control type 2 error. Okay. All right. So suppose we have H0 is, let's say, mu equal, let's call it mu 0. HA is mu greater than mu 0. And let's let alpha equal, alpha is the probability of type 1 error, so we'll set alpha equal to, so alpha we know what it is, and beta, let's set beta equal to a particular mu a. So the alpha is equal to probability, choose HA given mu equals mu 0, and let's set beta equal beta mu equals mu a. Probability, choose H0 given mu equals mu a. Okay, type 1 and type 2 error. Then alpha is equal to probability y bar is greater than k given mu equals mu 0, which is equal to the probability z is greater than, what's the mean of y bar? Same as the mean of yi, so it's mu 0. So k, subtract off the mean, divide by the variance of y bar, so the square root of it. So divide by square root of theta squared over n, so theta, and I get the square root of n there. So it's the probability, alpha is equal to this, the probability that z is greater than this, which implies that k minus mu 0 over sigma square root of n is equal to q norm 1 minus alpha, or k equals mu 0 plus sigma over square root of n q norm. All right? Okay, that's right. Also, if I do the similar maneuver for beta, we have beta is equal to probability y bar is less than k, given mu equals mu a, which is equal to, I should be writing approximately here, right? So this is approx for z and z. Okay, so this approximately equal to the probability that z is less than or equal to k minus mu a over sigma square root of n, which implies if I want if since this is beta is equal to this probability, so this is the same thing as saying that K minus mu A over sigma square root of n is equal to Q norm beta, right? Or K equals mu A plus sigma over root n Q norm beta. All right, so if both those things are true, this means I have two different expressions for K, and I can set them equal to each other. And if everything else is known, I can solve for n. The K will disappear. In other words, I really have two equations, two unknowns here. So I have alpha is known. It's set something, right? We're going to take beta to be known, a certain probability that it is once alpha is set. So that's known. And sigma is known, approximated or known. Mu A is known. Mu 0 is known. So everything's known except for K and N. We're letting n wander. And I suppose you could look at n as fixed and beta unknown, but yeah, we're going to look at everything as fixed except for K and N. And in this case, we can now set the two expressions for K equal to each other, right? So setting the two expressions for K equal to each other, we have lots of things should cancel here. So let's see, I have mu 0 plus right is equal to mu A yeah, or let's clean it up, bring mu A to one side, maybe subtract, so I get yeah, so what do we get? We get subtract, so I get over here, I get mu A minus mu 0, and over here, if I subtract, yep, I get sigma over square root of n Q norm 1 minus alpha minus Q norm beta. Okay, that's equal to that, I think. Subtract, yep. And so we have n is equal to multiply, divide, I get sigma squared Q norm 1 minus alpha minus Q norm beta, all squared, divided by mu A minus mu 0, also all squared. Yep. Okay, so for example, for the tire problem, suppose we had n tires unspecified, sigma squared was approximately 10 to the 6th, and say mu 0 was 20,000, and suppose mu A is equal to 19.5. If we want, suppose before we only asked for like a 0.05 alpha and a point, and we didn't specify beta. So if we want, now we can specify what we want. We just have to make n high enough. So if we want alpha equals, say, 0.01, only a 1 in 100 chance of making an error, type 1 error. Oh yeah, so the test is H0 mu equals mu 0, and versus HA mu is less than mu 0. Okay, and the rejection region was, of course, was y bar we reject less than k, right? Y bar less than k was the RR. Now I would have to reset k from the last value because I'm changing alpha to be 0.01. K is based on alpha, but that doesn't change this equation here for n. Okay, so k is based on alpha, set k. Now, if I want to additionally specify beta, well, I can, and I can keep alpha what it was, and all I have to do is increase n here. So, okay, so we're here, so then n, take n equal to alpha squared, 10 to the 6th. So this was actually s squared was 10 to the 6th. So we approximate it with 10 to the 6th. Q norm 0.99. Do you know what this is? Q norm 0.99? It's 2.33 minus Q norm 0.05. This is going to be negative 1.645 or something like that, 1.645 squared over mu 0 minus mu a squared. So this is 20,000 minus 19. So this is 500 squared. 500 squared is 25. 2 zeros out. 500. 25. I think so. Okay. This doesn't seem right. Yeah, no, it's right. 25. Sorry. Okay. All right, so there we are. So we take n equal to this. I get, when I do this, actually, you can see this is just 4 here. So we get about 4 times 15.77, which is about 63.1. So take n to be the next biggest integer, 64. So we had it about right. But this is a more careful way to do it, and we can do it in general. Okay, could you do one of these? Yes, you could. You have the formula. You could derive the formula probably too. Okay, that's it for calculating type 2 error and sample size for large-scale tests. Next lecture will be on small sample size tests. Okay, thanks.